Step change response of a piano string. Okay, here's our cartoon showing what we're talking about. I'm going to make a sudden step downward at the graph end of the string. It's under tension. And in this particular case, it will be an A2 like string, and it's going to be 0.9 meters long. And the step will be 1 millimeter. It's described by the stiff wave equation, where y is going to be the vertical displacement, t is the time, x is the position along the string, c is the propagation speed of the flexible string, and it's about 200 meters per second. E is the elasticity parameter. Depends on the Young's modulus, the tension and the diameter. Tension is about 721 newtons, and you already talked about the length. The time to propagate across the string from the graph to the bridge will be equal to the length divided by the speed if it were a flexible string. And in this case, it will be 0.9 meters divided by 198 meters per second, which calculates out to about 4.5 milliseconds. Now, we're going to look at it three different ways. First way is numerically. We're going to we're going to discretize the x, the t, and the displacement. The second derivative with respect to time is going to be replaced by this. Second derivative with respect to distance here. The fourth derivative by this expression. And when you plop that in the stiff wave equation, you get a recursion expression here for the displacement at the n+1th time as a function of displacements at n and n-1 times and other positions along the string at those times. You solve it, you get this kind of response. I'm plotting displacement versus position along the string, 0 to 0.9 meters, and looking at about the first 7 milliseconds. You see this first snapshot, which is probably around 0.3 milliseconds. You see the step has been made, and it generates ripple for a while, and then the other half or other portion of the string is at the original quiescent value of 0 displacement. So you can see there's ripple, and there's a little burst of really high frequency material here, and then nothing. Then as time progresses, here's the next step here, next snapshot. And the next snapshot shows that now the hash is propagated all the way to the bridge, and we still got the ripples. And as time goes on, the hash seems to take over. Here, for example, at 4.5 milliseconds, it gets reflected and goes back the other direction. And by about 7 milliseconds, it's a lot of hash. But there's also an underlying ripple. Now here's a snapshot of 0.3 milliseconds, I'm sorry. So here's the step down. And the step down is propagated a little bit, and then it's caused ripples in the rest of the first half of the wire. And you see you got the ripples here, and then this kind of strange looking hash. At 6 milliseconds, the hash is really come into being. And of course, this is on the way back now. This is after we've been reflected off of the bridge. There's some more snapshots. You can see the hash is starting to dominate. You can also look at a spot along the string, in this particular case, 0.3 meters, and watch the evolution of the signal at that spot in time. So here, for example, we were sitting on the string at 0.3 meters, and we see for about 0.2 milliseconds, we don't get any response yet because it hasn't reached that spot, 0.3 meters. But then we start to get some high frequency, and then the frequencies tends to slow down, get smaller, and then we develop some interesting hash. And then by 1.5 milliseconds, the step has passed the 0.3 meters by, because 0.3 divided by 198 is about 1.5 milliseconds. Okay, so it's kind of a inverse chirp. It starts out fast and then slows down. So these results are kind of perplexing. First of all, we see dispersion, which probably comes from elasticity. And then we see some dispersion, which probably comes from the numerical method used to solve the PDE. And so to get more insight into this, let's remove the elasticity. And now we watch the step progress. Here's the early snapshot. And you can see the step moving down as time progresses. When it gets down here at 4.5 milliseconds, it gets reflected and comes back. Now, what's interesting to me is how sharp these turns are, even though we're using the stiff wave equation and we're solving it numerically. The only difference is we don't have that fourth order partial derivative with respect to distance in there, which is probably amplifying a lot of the high frequency noise. All right. Here's two snapshots. The step going right and the step going left. Now, we know this isn't realistic for a couple reasons. First of all, you really can't make that step happen as quick as that graph shows, because it happens instantaneously. And piano strings are elastic, so you're not going to get this kind of response with a real piano string. Let's put a filter on the step, see what happens. And I started out using a first order filter, which is shown here in blue. And I displaced it a little bit for this graph because the filter I end up using, which is the sigmoid filter, requires some time to get going. So I found the parameters in the sigmoid by trying to match it up with this blue line. So the sigmoid has a nice feature that the derivative is not discontinuous. See, here's the derivative in red, and here's the actual curve. So it's going to be a smoother takeoff, and as a consequence, we get, instead of this over here on the left, we get this. So you can see here's that first early step up. You can't tell much from this graph, but there's a little bit of a overshoot, but it's up and around the corner, smooth. And then as time goes on, you start to develop some ripples, but there's no hash. So we smoothed out the step and we have gotten rid of the hash. Here are 4 responses that we've got so far. We first look at the red, which is the case where there's no elasticity and no filter. And when that goes to the blue, where we apply the filter, comes up smoothly and lines out. So the step response is smooth when you have no elasticity. Then the black is that first one we got, where we have elasticity and no filter, and it comes up and develops these relatively smooth ripples. It starts out at a high amplitude, low frequency, and then starts to speed up and lower its amplitude. The green is when we add the filter with elasticity. You see it comes up and it might overshoot. Yeah, it overshoots a little bit, but it's quite smooth. Okay, let's try to get more insight by solving the semi-infinite string. In other words, just relax the idea of L being finite and let it go to infinity. And this will allow us to use some transform methods. I'm going to use the Laplace transform to transform distance into the Laplace transform variable. I'm going to solve it for time, and then I'm going to use the Week's method to invert that transform. But we're only going to be interested in times up to 4.5 milliseconds because that's when everything hits the bridge and would get reflected, which of course there's no bridge for this particular model. All right, here's our model. The same as before, except we have an infinitely long string. It's a thought experiment because it really can't be done. Okay, so I'm going to apply the Laplace transform to the stiff wave equation and take x into p. If I do that, I get cap y, and then I get these two derivatives. Second derivative goes into this expression, and we're going to apply the boundary condition here. This is the step. In this particular case, the step is negative, minus 1 millimeter. And we're also going to specify that the slope is 0. Here's the Laplace transform of the fourth derivative. And now we have, again, the boundary condition at a graph, which goes into this. But we also then specify these three derivatives are 0. So by doing this, setting these derivatives to 0, we're really causing the response to be smooth. And if we do that, we end up with an ordinary differential equation in time, which we can solve. And if we do that, we get this expression. B is the step size, and then E is the elasticity parameter. So here's the Laplace transform as a function of P. And you can see that when E is equal to 0, you get this expression, which is just a moving step. So it's kind of consistent, kind of makes sense. So we're going to make the inversion using the Week's algorithm. If we do that, we get this kind of response. You can see the first step down, and there's the ripple. And then the second step takes a little longer, and then we get the ripple. And as time progresses, the ripples start to get a lower wave number, but there's no hash. For example, here's two snapshots. You see here at 1 millisecond, you see because of the speed of 198 meters per second, it reaches about 0.2 meters after 1 millisecond. You see we got the ripples start to decrease in wave number and also decrease in amplitude. And here's the snapshot at 3 milliseconds. And of course, we'll also take another look at the response if we pick a spot along the string, again at 0.3 meters. And if we do that, we get this kind of response. A little bit of hash, but real small amplitude stuff. And then we get a shot of high frequency. And then now, since we're dealing in time, we can talk about frequencies instead of wave numbers. And we get a increasing amplitude, decreasing frequency. And I tried to do a spectrogram of that ringing portion, and I wasn't successful. So I went ahead and just wrote a script to find the distance between the peaks. Oh dear, I lost some place here. The distance between the peaks here. And you can see that it starts out, the peaks are relatively close together, and then they start to spread out, which we saw. And then I can invert this distance between the peaks to get a kind of a frequency, which I show over here. So basically, you could say, well, it starts out at about, say, 130 kilohertz and ends up at about 6 kilohertz over a period of about 1 millisecond. So it doesn't last long, and it's at frequencies that will be well beyond the hearing range. Okay, let's do one more shot at this. Let's solve it for the finite string, but we're going to use a finite Fourier series. Actually, a finite Fourier sine transform. Excuse me. So here's our stiff wave equation. We're going to use the finite Fourier sine transform and get it into a variable function of n and t. In other words, x will go into n. It'll be an ODE. We'll solve that by Laplace transform and get y hat here, which will now be n and s because s will go into, t will go into s. We'll invert the Laplace transform to get this, and then we'll invert the finite Fourier sine transform to get y of x and t. This is the definition of the finite Fourier sine transform, integrated from 0 to L. The inverse is kind of different from the Laplace transform. You don't have a complex inversion interval to deal with or tables. Instead, if you can find the transform, you just plug it into this infinite series. So it appears to be simpler, but we'll see that there's some problems. Okay, the derivatives are a little bit different than with the Laplace transform. Here, the finite Fourier sine transform of the second derivative with respect to position is given by this expression up here. And if we apply the boundary conditions, this is 0. This is equal to b, the step, right here. And then we have this term here. No derivatives yet. If we look at the fourth derivative of the finite Fourier sine transform, we get this expression. For now, we have second derivatives at the boundaries. And we're going to specify that this and this are 0. We're going to specify that this is 0. And then this will be equal to b, the step. So it shows up here. And then we'll have this term here. So we end up with an ODE for cap y here in red. And we can select these coefficients and write it like this. Second order ODE, pretty simple to solve. I'm going to use the Laplace transform to solve it. If I do that, I get this expression here, which you go to the tables and you find that it's given by this expression. So here is the finite Fourier sine transform as a function of t and n. And we plug that into the infinite series, do some algebra, and we end up with this expression for y of x at t. And here's two snapshots. There's a snapshot at 0.3 milliseconds. You can see it looks like the others, kind of, but it's got hash in there. See, here's some, and here's some. And then it develops into some more hash down here. At 3 milliseconds, it's got quite a bit of hash going on. I used 1,000 terms in the sum, and it, when you get out into that particular number, it doesn't make much difference if you increase it or decrease it around 1,000. You're going to get the same kind of response. You can compare the three. If you overplot them early on here, they look about the same. This is for taking a snapshot uh, at 0.3 milliseconds. The S didn't come through here. At 0.3 milliseconds, this is a snapshot along the string. You take a closer look at that first peak right here, and you see that the finite difference approach is shown here, relatively smooth. The semi-infinite solution is green. It's smooth, quite smooth. And then the finite Fourier sine transform is in red, and you can see it bounces around the semi-infinite solution. Here's three other shots. Finite differences, semi-infinite string, and the finite Fourier sine transform. They look pretty similar. This one is the finite Fourier sine transform is disappointing to me because I was hoping for less of the hash. Okay, so in conclusion, we can say those ripples may be real, but they appear to depend on the smoothness of the step. And also they occur over quite a short time interval, and they're at high frequency or high wave number. You're not going to be able to, I don't think you're going to be able to see them particularly easily if you could even concoct an experiment. The finite difference approach generates what appears to be numerical dispersion, but also that it shows up in the infinite series solution, which is kind of a puzzle to me. I don't understand that. Semi-analytical solution for the semi-infinite string is smooth, has no particular numerical dispersion, but it does show the physical dispersion. But in the process of developing that solution, you do specify that first, second, and third derivatives with respect to position at the boundary are zero, which may be a little bit unrealistic. And then we've noticed that as time goes on, the spacing between the ripple peaks increases. So that's about all I can give you on this. I wish I could tell you more. Thanks for listening and watching.